Welcome to the visit training session titled Utilizing Synthetic Imagery from the NSSL 4-Kilometer WRF ARW Model in Forecasting Orographic Cirrus. My name is Dan Bicus. I put this training session together, and Dan Lindsay played a major role in bringing the data to CIRA, along with the other folks listed here. This training session is part of a series that focuses on applications of synthetic imagery from the NSSL 4-Kilometer WRF ARW Model. Forecasting orographic cirrus is important because of their influence on temperature forecasts. Utilizing synthetic imagery generated from a model is a useful way to anticipate orographic cirrus. Orographic cirrus can be more easily visualized on synthetic imagery compared to model output fields that you've been used to looking at, such as relative humidity over some layer. In this training session, we'll focus on orographic cirrus, which develops in a stable atmosphere where you get a wave that's produced by the mountain range, depicted down here, and is transmitted to the upper levels, which we see up here. If there's sufficient moisture at upper levels, orographic cirrus can develop and sometimes can be quite thick. And this is what we're talking about up here, this shaded area. Although this forms sometimes, what we're going to talk about mainly in this session is this orographic cirrus that forms along and downwind of mountain ranges. And the big forecast implication here is the temperature forecast. Since the source of the cloud cover is stationary, this makes it appear readily in satellite imagery and thus in synthetic imagery as well. Synthetic imagery is model output that is displayed as though it is satellite imagery. Analyzing synthetic imagery has an advantage over model output fields, such as relative humidity over some layer, and that the feature of interest appears similar to the way it would appear in satellite imagery. There are multiple sources of synthetic imagery available on the web. For example, the CRAST model at the University of Wisconsin has been available in AWIPS via the LDM for some time. The primary focus of this training session is synthetic imagery generated from the NSSL 4-Kilometer WRF ARW model. The model is run once a day at 0Z. Certain model output fields, including cloud water, cloud ice, temperature, water vapor, and so forth, are sent to CIRA and SIMS. These WRF outputs are used as inputs to a model that generates the synthetic imagery. Gaseous absorption is calculated for cloud-free grid points, and modified anomalous diffraction theory is used to obtain scattering and absorption by the cloud particles. The model outputs brightness temperatures for a number of satellite bands. For additional information about the details of the model, see the references on the Student Guide webpage. Remember, the model is run once a day at 0Z. Hourly output for the 12 to 36-hour forecast, valid 12Z of day 1 to 12Z of day 2, is made available. The bands are those that will appear on GOES-R, since the project is based on demonstrating products that will be available on the GOES-R satellite, scheduled for launch around 2015. The bands are very close to those found on the current GOES satellites, so that the principles discussed in this training session readily apply to operational GOES satellites of the present. We'll be talking about the water vapor band and the IR band. On the left is the synthetic imagery for the IR band from the WRF ARW model for December 3rd, 2010. The times are 0 to 6Z December 3rd, which means this is from the 0Z to December run. On the right, we have the corresponding GOES imagery. These are time-matched, and the times correspond right here. Remember, in GOES satellite imagery, orographic cirrus appears as brightness temperatures that originate over mountain ranges and advect only in the downwind direction, with the source region of the clouds being stationary as it's tied to the mountain range. In this example, the model has what appears to be orographic cirrus downwind of the Sierra Nevadas in California, advecting into Nevada. Here in Idaho, downwind of the Silver City Range. In Wyoming, downwind of the Absaroka and Bighorn ranges, and in Colorado, downwind of the Front Range and the Sangre de Cristos, down here to New Mexico. The model appears to do a pretty good job with developing the orographic cirrus downwind of the Sangre de Cristo and Front Ranges that we see later in the loop over here in the GOES imagery. The other regions had orographic cirrus present in the model during this period, which is shown across Nevada, but not as much downwind of the Absaroka and Bighorn ranges in Wyoming. In Idaho, there's high-level cirrus advecting across the region, making it more difficult to assess how much of this was orographic cirrus. Just like looking at any other model output, there will be times that it performs well, and other times not so well. Poor initialization, lack of resolution, and other familiar sources of model error will show up in the synthetic imagery. Let's compare the 6-hour NOM temperature forecast with the observed values from the RTMA at 6Z. That's the end of the loop in the synthetic imagery we just looked at. The major feature by 6Z was the development of orographic cirrus downwind of the Front Range and Sangre de Cristos in Colorado and New Mexico. The RTMA, if we look at this, has warmer temperatures than forecast. So here's the NOM, and here's the RTMA, and you can see warmer temperatures than forecast, particularly in this area here, which is underneath the orographic cirrus that was developing there. And this is likely due to some combination of the orographic cirrus keeping it warmer at night, along with downslope winds. Now we switch to a different case. This is for January 5 and 6, 2011, in a situation with a tricky low temperature forecast in Montana. The synthetic IR imagery shows orographic cirrus developing in the evening hours and persisting overnight downwind of the Lewis Range and extending up into Canada. So it's this feature right here that we're looking at. The timing of this would keep the temperatures warmer than expected and result in a warmer minimum nighttime temperature forecast. Looking at the verifying GOES IR imagery, we see that orographic cirrus does develop here downwind of the Lewis Range about the same time as predicted by the WRF ARW model. The cloud cover also persists overnight as was forecast. Here's the NOM temperature 6-hour forecast valid at 6Z from the 0Z run. The NOM shows values in the upper 20s to low 30s downwind of the Lewis Range here in Montana. And then we go to the RTMA at that time, and we see values that are about 5 to 10 degrees warmer than forecast downwind of the Lewis Range and extending up here into Canada. Here's the NOM 12-hour forecast temperature valid at 12Z, still looking at the 0Z run. And we see values here in the upper 20s to low 30s for the most part in the region of interest. And we skip ahead to the RTMA at 12Z, and we see values still in the upper 30s to low 40s in this same region. So it appears that the orographic cirrus played a significant role in keeping the temperatures warmer overnight and into the next morning, making for a warmer minimum temperature forecast than what was forecast by the model. Keep in mind that downslope winds may have contributed as well. In the next case, we'll consider multiple factors in addition to the orographic cirrus that can play a role in the temperature forecast. Now we switch to a different case. This is for November 18th, 2010. And we'll start with the traditional approach of analyzing model output for orographic cirrus potential by looking at GFS 300 to 500 millibar layer relative humidity. And you can see the general trend is for this increasing relative humidity from Northern California over to Wyoming. And it's more difficult to assess which of this is synoptic scale cirrus versus where is the orographic cirrus that may be developing. For example, note this area downwind of the Front Range here in Colorado, where we see a trend of increasing relative humidity. So we'll look at this area in quite a bit of detail as we go through this case here. Now let's analyze orographic cirrus potential over the same time period by looking at the WRF ARW synthetic imagery. Some of the differences you should notice are that you're now looking for what appear to be orographic cirrus, the way you're used to diagnosing them in satellite imagery. It's much easier to focus in on regions where clouds originate from a mountain range as opposed to looking at trends in relative humidity. The temporal resolution is another advantage, offering hourly images as opposed to the model output, which is at 3 or 6-hour intervals, depending on if you're looking at the NOM or GFS, for example. The imagery shows what appear to be orographic cirrus, either present or developing in western Nevada and California, southwest Idaho, northern Wyoming, and central Colorado, downwind of many of the mountain ranges we looked at earlier. Here is the crass synthetic IR imagery for the same forecast period. The resolution is more coarse than the WRF ARW. However, it is good practice to look at other models the same way you look at the operational models and ensembles to gain confidence in your forecast. In this example, it appears that there is generally an agreement on where orographic cirrus will develop between the crass and the WRF ARW models. Synthetic water vapor imagery is also available from the WRF ARW model. This can be useful in looking at the general flow pattern, and in the case of orographic cirrus, you will oftentimes find regions of subsidence over the mountain region of interest, with orographic cirrus advecting in the downwind direction. For example, here in downwind of the Front Range of Colorado, you can see a dark region. You can see a dark region here in the Wind River Range, the Absarokas, and the Bighorn Range of Wyoming. So this signature can also be useful in looking for orographic cirrus. Here is a cross-section of the GFS relative humidity field over the Front Range of Colorado. It's important to note that we're not suggesting synthetic imagery replace analysis of model output fields, rather to complement one another so that you may assess confidence in a forecast of orographic cirrus. For example, we earlier identified the potential for orographic cirrus in the WRF ARW and crass synthetic imagery over the Front Range of Colorado. Now we look more carefully at that region, looking at the GFS relative humidity field in a cross-section. Using this method allows you to check various models and allows one to assess confidence in the location and timing of orographic cirrus development. Here is the GOES IR imagery during the period of interest. Note that synthetic imagery did a pretty good job in identifying where and when orographic cirrus would develop. The timing of the development of orographic cirrus can be crucial to the temperature forecast. For example, notice the developing orographic cirrus across the Front Range of Colorado during the late morning hours, which would significantly reduce insolation during a key time of the day. Here's the GOES water vapor imagery during the period of interest. Note the region over the mountain range, such as the Front Range and the various mountains up here in Wyoming, where orographic cirrus developed, is usually darker, in other words, warmer brightness temperatures, than the region around it due to subsidence. Although the signature is not as pronounced as in the WRF ARW synthetic imagery, it's still there, and it's actually a good thing that it kind of stands out more in the synthetic imagery and that it catches your attention more readily. Here's the visible imagery zoomed in over Colorado. A combination of the lack of downslope winds and insolation due to developing orographic cirrus resulted in a colder region in north-central Colorado along and just east of the Front Range. So we're talking mainly about this region right in here. The morning inversion held on in regions where the winds were calm and insolation was significantly reduced. The result were temperatures that were well below Moss forecast high temperatures. Temperatures warmed up where insolation occurred, or there was sufficient downslope flow to erode the morning inversion. Usually the temperature forecast comes down to some combination of factors like we see in this example. Here is a picture of the orographic cirrus over Fort Collins, Colorado at 20Z November 18th. And notice these are relatively thick orographic cirrus, which significantly reduce insolation. Here's the RTMA temperatures and winds that goes along with the visible loop that we just looked at. Note the pocket of cooler temperatures, approximately in this area right here, under the region where orographic cirrus developed. After sunset, the area under the cirrus would cool down more slowly compared to clear sky conditions. At times, the synthetic imagery may look unusual. For example, here is the synthetic imagery from the WRF ARW for December 7 and 8, 2010. This is 2 days' worth of imagery with a gap between 6 and 12Z. The unusual aspect of this case are the long lines of clouds that don't appear natural. Let me just go ahead and highlight those. This is the feature I'm talking about, these long streaks across Nevada, Utah, Arizona, and if we continue the loop here, it spreads over towards the east. The long streaks correspond to thin cirrus that are optically thicker in the model than observed. You will have to mentally block out the long streaks of clouds when you come across this type of situation. One way to more easily identify the orographic cirrus is to turn up the loop speed and rock it back and forth. Doing this, you can readily identify orographic cirrus since it's originating off various mountain ranges and only advecting in the downwind direction. For example, you can now readily pick up the orographic cirrus downwind of the Sierra Nevada range in California, the Lewis Range in Montana, and in Wyoming downwind of the Absaroka and Bighorn ranges, as well as the Front Range of Colorado later in the loop. Here is the corresponding synthetic water vapor imagery, and as before, we can increase the loop speed and rock it back and forth, and that will allow us to more readily identify the regions of orographic cirrus. Also, we can make use of the unique aspect of the water vapor imagery, and that is these dark regions, these warmer brightness temperatures that often form along the mountain ranges and are a signal of the subsidence. For example, we see this signature right here along the Sierra Nevada range in California with orographic cirrus developing downwind of that. And then over here in Colorado, we see another one of those signatures, the darker signature that we see across the mountains. Here's the verifying GOES imagery. By mentally subtracting the erroneous long lines of clouds that we looked at in the synthetic imagery and also turning up the loop speed, rocking it back and forth, we're really able to focus in on where the orographic cirrus developed, and then we can see that the model did actually a pretty reasonable job of depicting the orographic cirrus. Where can you view the synthetic imagery? The WRF ARW imagery we've been showing is part of the GOES-R Proving Ground products that are available in AWIPS via the Central Region LDM. If you're outside of Central Region and desire this data in AWIPS, please contact us. The imagery is available also on the web at CIRA at this URL. And make sure you select the synthetic imagery from the suite of other GOES-R Proving Ground products. SIMS also makes the imagery available at the URL shown here. Remember, CRAS synthetic imagery at a coarser resolution is also available via the Central Region LDM. Go to this link for instructions here. And finally, if you're interested in model output fields from the WRF ARW model, it's available right here. Synthetic imagery analysis and forecasting orographic cirrus does have advantages. Orographic cirrus is more readily identified compared to looking at model output fields such as relative humidity. Also, there's increased temporal resolution. It's available hourly rather than at the various model output times listed here. The best approach is to look at multiple sources of synthetic imagery to readily identify regions of orographic cirrus, then look more carefully at those regions, utilizing multiple models to gain confidence in the occurrence and timing of orographic cirrus, and most importantly, what effects they may have on the temperature forecast.